At its core, precision machining is the continuous application of localized force. A workpiece is secured in place, while a rigid, metallic cutting edge is driven against it to permanently shear away material. Regardless of the control system dictating the movements, the efficiency of this process relies entirely on managing extreme mechanical forces, thermal friction, and exact geometric alignment. For decades, manufacturing relied on a strict historical baseline. This volatile physical action was governed exclusively by human kinematics and direct mechanical linkages. Engineers define this as an open-loop architecture. The operator establishes the feed rate and the cutting speed by relying on fixed gear ratios and their own intuition. Because there is no automated system to sense and correct errors mid-cut, the maximum throughput is strictly capped by the physical limits of human reaction time. The traditional engine lathe serves as the definitive archetype of this open-loop architecture. To absorb the violent vibrations generated by cutting metal, the machine requires a massive foundation, a seasoned, high-compressive strength cast iron bed. Inside that casting, heavy-ribbed internal construction and machined V-slides ensure the structure maintains absolute alignment under extreme stress. Power delivery is mechanical. The headstock houses a spindle driven by stepped pulleys, locking the workpiece into fixed speeds. To execute the cut, the carriage is driven along a threaded lead screw. This motion depends entirely on physical gear engagement and manual handwheels. Because the cutting tool's path is physically bound to these specific gear ratios, the system cannot react. If the tool hits a pocket of harder metal, the lathe will not adjust. It physically lacks the capacity to adapt. Computer numerical control, or CNC, severs this physical dependency on gears by replacing mechanical linkages with continuous streams of data. The central processing hub is the machine control unit. It decodes programs into precise access motion commands for the drive amplifiers. This creates CNC's defining advantage, closed-loop feedback. Transducers continuously monitor the cutting tool's velocity and position, feeding data back into the MCU. This continuous data loop allows the MCU to instantly compare the programmed theoretical path against the actual physical position of the tool. It calculates microvariances and applies real-time servo corrections faster than human perception. The MCU utilizes spatial interpolation to calculate complex multi-axis trajectories simultaneously. The MCU distributes control signals to specific drive motors. Horizontally, ball lead screws move the machine table across the X and Y axes. Vertically, an independent motor drives the spindle along the Z-axis. Operators can manually override these axes using the jog interface. By coordinating independent servo motors through spatial interpolation, the machine executes smooth, complex curves and geometries that a manual hand-cranked carriage could never accurately replicate. A flawless digital command is only half the process. Overall efficiency is still strictly governed by the physical mathematical relationship between cutting speed, feed rate, and the depth of cut. This formula calculates the exact spindle cutting speed, represented by S, required for optimal material removal. The variables are rigidly tied to D, the geometric diameter of the workpiece, and N, the rotational speed in RPMs. These values are constrained entirely by the metallurgical class of the workpiece, the material of the cutter, and the specific tool geometry. An engine lathe operator is locked into the closest approximate speed offered by their stepped pulleys, but a CNC's machine control unit dynamically modulates RPM and feed rates to maintain the exact mathematical optimum throughout the entire duration of the cut. Yet, despite infinite digital precision from the MCU, the machine operates in the physical world. Mechanical stress and material variance will still force systemic machining errors. The most destructive acoustic and physical failure state is workpiece and tool chatter. It manifests as a violent shudder at the cutting edge, tearing a rough, rippled pattern into the steel. Chatter is an issue of severe harmonic resonance. It occurs when the frequencies generated by the machining process synchronize with the natural frequency of the workpiece material. Diagnosing and fixing this requires restoring physical rigidity to the system, adjusting the drive belt tension, ensuring high pressure on chuck clamps, and tightening loose slide jibs. On the software side, operators must rewrite the MCU instructions to alter the ratio between RPM and feed speed, purposefully breaking the harmonic resonance. Closed-loop digital error correction is useless if it is fighting against a loose, vibrating, or poorly maintained mechanical chassis. The digital precision of CNC requires massive initial capital expenditure and carries high maintenance costs for its delicate network of transducers and drive amplifiers. This economic reality is why the manually operated engine lathe remains highly viable. For low-volume or custom prototype work, an open-loop cast iron machine is often the most cost-effective option, but for high-volume industrial production, CNC technology maximizes throughput. By utilizing predictive design software and continuous closed-loop feedback, it guarantees exact dimensional accuracy across thousands of parts, driving the per-unit cost down significantly. The machine control unit provides a perfect mathematical brain, but whether the cut is guided by a microchip or a machinist's hands, all precision manufacturing remains permanently bound by the physical rigidity of its cast iron foundation and the uncompromising metallurgical limits of the cutting tool.
Thanks for watching, and please like, share and subscribe for such more content and appreciation. Make sure to comment your questions and